In section 2, we look at non-standard normal distributions. And the idea is if it is a normal distribution, but it does not have a mean of 0 and a standard deviation of 1, we can find the z-scores of all the values in that distribution and basically turn it into a standard normal distribution. In other words, there is a one-to-one correspondence between the two. And this will allow us to go ahead and then use our table 4, the standard normal distribution table values, to find the areas. So really, this is a quick section. It's just about, hey, take the values you have, find your z-score, and then, because they're both normal distributions, you can go ahead and use that. So, for example, we want to convert the specific x value that borders a shaded region into a z-score, and then use table 4 to find the desired probability. For example, the heights of men are normally distributed with a mean of 69 inches and a standard deviation of 2.8 inches. What percentage of men has a height less than 80 inches? The standard door height. Well, here's our z-score. We take 80, subtract the 69, so we're using this equation there, divide by the 2.8, and we end up with 3.93. 3.93 is beyond our table of 3.5, and so for everything beyond it, we just use 0.9999. It is possible to actually do a direct calculation of that area, but we're not going to worry about that. We're just going to usually use the table. So, let us look at some quick examples. Here, we have a couple of pictures of the normal distribution of IQ scores. Okay, mean of 100 and a standard deviation of 15. So again, these are non-standard normal distributions because they do not have a mean of 0 and a standard deviation of 1. But what we can do is go find the z-scores of the indicated values. So this is an IQ score of 125. We convert it into a z-score of 1.67. Over here, we have to do it twice, once for the 75 and once for the 110, to find the z-scores associated with those x values. Then we can go use table 4. In this case, since the area is to the left, read it off the table. That shaded area would be almost 95%, 0.9463. Over here, since there's 2 of them and we want the area in between, we would find the area for each one. So the first one, the area was 0.0475, which would basically be like this little unshaded part. The other one, going up to 110, that was 0.7486. Subtract, and the area that's in between those two z-scores, which is in between those two IQ values, would be about 70%. Now, sometimes you'll get pictures or descriptions, but sometimes you'll actually have something that's more like a word problem. So let's look at an example for that. The Gulfstream 100 is an executive jet that seats 6, and it has a doorway height of 51.6 inches. And men's heights are normally distributed with a mean of 69 and a standard deviation of 2.8, just like our example above. Women's heights, on the other hand, are normally distributed with a mean of 63.6 and a standard deviation of 2.5. What percentage of men can fit through the door without bending? What percentage of women? So we're going to do the same kind of thing. Turn each of those into z-scores. For the men, 51.6 is well below 69, so we actually end up 6 standard deviations, more than 6 standard deviations less than the mean. For women, it's almost 5 standard deviations less than the mean. Both of these are much less than z equals negative 3.5, and so we would use an area of 0.0001, which is basically 1% of 1%, 0.01%. So pretty much nobody on average would be able to fit under the through that doorway without having to bend over a little bit. And again, 5 feet tall is 60 inches. So at 51, you're almost 9 inches shorter than that. So That's like 4'3", so not very many men and women are of that height. Now, here's a second example. The U.S. Marine Corps requires that men have heights between 64 inches and 80 inches. Find the percentage of men that meet that height requirement. Are many denied the chance to become a Marine due to their height? There was a basketball player a few years ago who was in the Navy, not the Marines, but he's in the Navy, and he played center for San Antonio, and so he was like 7 feet, which would be more than the 80 inches, but he could still be in the Navy. But definitely some occupations in the military, like being a fighter pilot, would have some height restrictions in that case. So again, we turn our various heights. 64 minus the 69 over 2.8, that's a negative 1.79. For the 80 minus 69, 2.8, that's a 3.93. Again, when we're above the mean, we get a positive z-score. When we're below the mean, we get a negative z-score. So we go look up table, and again, just to show for the negative 1.79, so here's negative 1.7, and we'd have to go all the way across for the 0.9, and so you can see that it's 0.0673. So that's how we get that one from the table. And then for the 3.93, well, 3.93 we got here at the bottom on this one that I made off with Excel spreadsheet. And so 3.93, as you can see, it's got 4 9s in it. So let's see, 1, 2, 3, so 0.9996. So pretty much 99.99% of all are under the 80-inch one. So we subtract between the two, and we end up with 96.32% of all men on average fit between those two heights, and so no, not very many are denied. And as I said, this is a short section. That's pretty much it. We are done with section 5-2.